So today we're going to be learning how to differentiate another kind of functions. That is a function that's actually just a product of two functions that we know how to differentiate. An example of this would be something like f of x is equal to x squared sine x. Now, if I asked you to find the derivative of this, it would be a little difficult. What most people assume is that you can just take the product of the derivatives of each individual function, x squared and sine x, but that's not actually correct. So in this video, I don't just want you to learn some formula. I want you to understand why the product rule is the product rule. And the product rule is actually pretty counterintuitive so I'm just going to write down what the product rule is in short. So if we have two functions, then let h of x be equal to u times v. If I ask you to take the derivative of u times v with respect to x, that would be the derivative of u with respect to x times v plus the derivative of v with respect to x times u. And this doesn't really make sense, and I would like to show you why the product rule is so. And a very good way to intuitively understand why certain formulae are the way they are is to understand how it might have been discovered. So let's look at this duv by dx. And obviously this uv is what's giving us a bit of trouble to actually take the derivative. All know this duv is basically a small nudge in the value of uv. And that nudge is infinitesimally small, but it still is a nudge. And a way to think about it is if we nudged each individual function by a small amount in a certain direction. We wouldn't just be able to write it as the product of two small nudges of each of those individual functions. If u plus du would be one small nudge of u, and v plus du would be another small nudge of u, then we could say that the small nudge of the product of u and v could be written as the product of these two nudges subtracted by the product of the value of the two functions at that point. And that kind of makes sense because I'm nudging this slightly and I'm using that value to take the product of the value of this that's already been nudged slightly and then subtracting it from the initial value. So what we end up with should be a small nudge in u and v. And that would obviously be by dx. So if we open this function out, we would get something like u times dv plus v times du plus du times dv, the whole thing upon the small nudge in x. And if you think about it, both du and dv are both very small values. And as you know, when we take the product of two extremely small values, it gives us a much smaller value. And we also need to keep in mind that this is eventually tending to 0. And since it's not being multiplied to anything else, but just being multiplied to another infinitesimally small value, it's as good as being 0 itself. So we can just write it as dv plus, so we can just write it as this. That's the reason why we can write it like this. And then this is exactly the same as u times dv by dx plus v times du by dx. And here we have an intuitive way of looking at the product rule. And the main thing to keep in mind is that this du dv would eventually tend to 0 and is negligible. But now you would think that that might be a little inaccurate, and it's probably not actually the derivative of the function. It's just an approximation to the derivative of the function. And that is why this du times dv is a little hard to understand, because sometimes we look at it as having a value, but it's actually infinitesimally small. And if we take a function that is w of x, which is equal to f of x times g of x, and we wanted to find w dash of x, that would just be the limit as h tends to 0 of w of x plus h minus wx upon h, right? And we've done this definition of the limit before. And now this can be written as, and that is just substituting this into this equation upon h as it tends to 0. We can add any term to any equation as long as we subtract it at the same time, right? And so the equation just remains the same in the end. So in that same way, we can subtract f of x times g of x plus h. And this is just a neat trick by manipulating algebra. And we're subtracting that, we're adding and subtracting the same term here, this whole thing upon it. So if we take g of x plus h common, we would get g of x plus h times f of x plus h minus f of x. If we take f of x common, we would get f of x times g of x plus h minus g of x. The whole thing upon h as h tends to 0. And if you notice, we can always just write it as g of x. We can always just write it as g of x plus h times f of x plus h minus f of x. And we can always just, the whole thing upon h, and we can always just write this as f of x times g of x plus h minus g of x, the whole thing upon h. And as h tends to 0. So this becomes two separate terms. And this, I'm going to mark it with blue, is actually just the derivative of f. And this is actually just the derivative of g. So this in turn, can be written as, I'm just going to write it up here. So this in turn can be written as, I'm going to write it in blue, g of x times f dash of x, because that is the derivative of f of x, plus f of x times g dash of x, because this is the derivative of g of x, and well, this is just the product rule itself. And that should clear any doubt about the previous proof that I had, the previous way of finding the product rule that I had shown you. Now, if we go back to the problem I had written here, which was f of x is equal to x squared times sine x, then we would be able to solve it using the product rule. So keeping in mind that duv by dx is equal to dv dx times u plus du dx times v, we can just solve this by making this f dash of x being the derivative of x squared, which is the derivative of x squared, which is 2x, times sine x plus x squared times the derivative of sine x, which is cos x. In that way, we can take the derivatives of products. So another derivative that might be difficult to take would be when two functions are divided by each other. So something like h of x being f of x upon g of x. However, this can be solved using a combination of the chain rule, which I had taught in my previous video, and the product rule. And that can be looked at as f of x times g of x raised to minus 1. So using the product rule, we know that the derivative of h of x would be the derivative of f of x times 1 upon g of x plus f of x times the derivative of 1 upon g of x. That this cannot be mistaken by 1 upon the derivative. It is the derivative of 1 upon the function. So you would have to use the chain rule in this case to take the derivative of it. So now this can be written as f dash of x upon g of x plus f of x, and so we can look at it as a composition of the function 1 upon x and g of x. So if w of x was 1 upon x, then it can be looked at as w of g of x. And so we would first take the derivative of 1 upon x, which would be negative 1 upon x squared. So we would make this, which would be negative 1 upon x squared. And then if we replace g of x instead of x, we would get this. And then we would have to multiply it by the derivative of what g of x actually is. So if we take the LCM of the two fractions over here, that would be to multiply the numerator and the denominator by g of x to make the denominators of both of them equal. We would get something like g of f dash of x times g of x upon g of x squared minus f of x times g dash of x upon g of x squared. And this is exactly what the chain rule is. So I'm going to write it down in terms of u and v. And since the numerator is equal, we can just make it one fraction. So if it was the derivative of u upon v, so d by dx of u upon v, that would be u dash times v minus v dash times u upon v squared. Because this is u dash, this is v, this is u, this is v dash, and then this would be v squared. Take an example. If we didn't already know that what the derivative of tan x was, how would you take it just knowing the derivative of cos x and sin x? So we would write this as sin x upon cos x, correct? And now the derivative of sin x is cos x, and the derivative of cos x is minus sin x. So now this can be written as the derivative of sin x, which is cos x, times cos x, right? Minus the derivative of cos x, which is minus sin x, times sin x, the whole thing upon cos squared x. Now this can be written as cos square x plus sin square x upon cos square x. And since cos square x plus sin square x is 1, that is a trigonometric identity, this would be 1 upon cos square x, which can also be written as sec square x.